answer for A that you just kind of went into automatic mode with is because the domains and ranges we've been looking at have been infinite sets. Because we've been looking at graphs of functions that either the graphs themselves or the graph that's defined by an equation. So most of you, when you looked at that set, in the back of your mind, you're looking at those individual points and you're saying, oh, that's f of x equals x squared. And so most of you wrote for the domain. Well, if you did, and you wrote the domain as -2 to 2, you would kind of have been not correct about that on a couple of different levels, because the domain for x squared is all real numbers. But the problem with writing brackets -2 to 2 for the domain here is that it suggests that you have an infinite number of points defined by this relationship. And there's only there's only 4 sets of points here, 4 ordered pairs defined by this relation. I haven't given you an equation for this. I haven't even given you a picture, but you could make a picture of this by simply plotting those 4 points. You can't connect them because you don't know how they're connected, if they're connected at all. But right now they just represent 4 individual ordered pairs. That's all they represent. Just like in class 12 when we looked at the 4 Boston Celtic players with their heights. And we asked, what are the inputs and what are the outputs? And that's how we began to define the domain and the range. So similarly here, the domain of this relation, I haven't even called it a function. The domain of this relation is simply a set of numbers. And those numbers are all the inputs that you see in the ordered pair. So in any order you want, I'm just going to go from smallest to largest. This is the domain of that relation. These are my 4 different inputs. Then the range looks at your different outputs. And just like the Beatles reunion, we didn't list John Lennon and Paul McCartney twice. Similarly, we only see 2 different outputs here, and they're 1 and 4, and we have to use our braces to denote that we're talking about a set. So anytime you're asked about a domain or a range, you always indicate the domain and range with a set. If it's an infinite set, then you look at either your set builder notation or your interval notation. But when it's a finite set like this, so we say this is a finite set with 4 elements. The elements are the individual ordered pairs. Okay. All right. Reverse the components for each ordered pair and write the resulting inverse relation. Why am I calling, when I write this, 4, -2, 1, -1, 1, 1, and 4, 2, as a set now of 4 ordered pairs where I've reversed the inputs and outputs, why am I calling it an inverse relation? The x's and y's are switched, the domain and the range are switched, the inputs and outputs are switched, and if I started here at -2 and went to 4, and then I came down here to 4, well, what would I be? If I came down here to 4, would I be -2 or 2? Oh, that's the problem, right? That's why I can only call it an inverse relation. Because the domain and range of the inverse, well, let's go there first before I show you the problem. What's the domain of this set right here? What's the domain? 1 and 4. So what's the domain of this inverse relationship the same as, this inverse relation? What's it the same? Yeah. The domain here is the same as what? The range of your first relation. They're exactly the same. And the domain for this inverse relation is, yes, thank you, the range. I do mean the range, thank you. Thank you, Bridget. So the range is -2, -1, 1, and 2. And again, we notice that the range of our inverse relation is the same as the domain of our relation. Okay, so the question comes up, is the inverse relation a function? So if we look at these four ordered pairs in part B, is that a function? No, because if I'm 4, I don't have a unique identity, right? 4 is mapped to -2 into 2, and we know that there's exactly one output for each input, exactly one output. And 4 right now goes to 2 different outputs. So the inverse relation is not a function. It's an inverse relation. So we say, nope, not a function. All right. A function, is this first setup here a function? -2 to 4, -1 to 1, 1 to 1, and 2 to 4. So here's a function. A function whose inverse is also a function. So not in this case. This is a function, but its inverse is not a function, it's a relation. But if we had a function whose inverse was also a function, we call that original function 1 to 1. Okay? We call it 1 to 1. So the relationship, I keep calling it relationship, the relation defined by this first set of 4 ordered pairs, is that a 1 to 1 function? Is this a 1 to 1 function? In other words, is its inverse a function? No, so it's not 1 to 1. Now later on in the demo and in your class activities, you're going to see a visual test for whether something's a 1 to 1 function. All right. And here's another way verbally to try to understand whether a function is 1 to 1. And you can tell just by looking at these 4 ordered pairs without any type of visual that it's not 1 to 1. A 1 to 1 function says if you have different inputs, you always have different outputs. Okay? So if you have different inputs, you always have different outputs. That's to be 1 to 1, not to be a function. This is certainly a function. This is definitely a function, but it's not 1 to 1. Because here I have, with -2 and 2, I have different inputs, but do I have different outputs for them? No, they both go to 4, which is okay. That's legal to be a function, because -2 goes to just one output. 2 happens to go to the same one. So it's legal as a function, but it's not 1 to 1, because the different inputs don't give me different outputs. All right? So it's a little tricky, the language for what makes something a function and what makes something 1 to 1. Okay, so this is the way that helps me think about 1 to 1. I say, okay, if I'm a different input, I have a different output. All right, so let's take a look at these 2 functions here. And we're going to answer the question of, does every function have an inverse function, and how can we tell? We already know the answer is no, because we just looked at a baby function with those 4 ordered pairs, and the inverse was a relation and not a function. So let's take a look at f of x equals x plus 1. If we were to graph that, what would that look like? Could someone tell me what the picture of f would look like? If I were to graph it really quickly here. F, right here, F. Yeah. Okay, so a horizontal line at 1 would look like this, Eli. It would just be a constant. So, but thank you. That would be, h of x is 1 would be a horizontal line through 1. But f of x has x plus 1. Yeah, so we start at 0, 1, which is your intercept, and we have a slope of 1. Okay, so we got that down. Whew. Okay, we got f. All right, what would g look like? Can someone tell me, first of all, what is the parent function for g? X squared. And what would have been the parent function for this one? y equals x, right? Just the straight line through the origin with a slope of 1. So here's our parent function for this one is the parabola x squared. And so what's happened? What's the transformation from x squared to this? What happened to this? Moved to over 1, but we have to talk about direction. To the right. Okay, so if I wanted to really get a quick graph of that, I don't have to plot points anymore. I've grown up, right? So we just go like this. There we go. There's G. All right. So right away we see two very different shapes. One is a straight line, one is a parabola. And we're going to investigate, does a straight line have an inverse that's a function? And does the parabola, the quantity x minus 1 squared, have an inverse that's a function? So if we picked 4 possible points from this line, 4 possible solutions, this is just 4 that make this equation true. When I put -2 in for x and add 1, I get -1, etc. So these are 4 possible solutions. And now I want to reverse the inputs and outputs. And this is what happens when I reverse the inputs and outputs. So now I'm looking at these new ordered pairs and asking the question, does different inputs produce different outputs? So different inputs, -1 brings me to a -2. No other input brings me to -2. So I'm golden with -1. 0 brings me to -1. Does anything else bring me to a -1? In these 4 ordered pairs? Nope. 1 brings me to 0. Nothing else brings me to 0. 2 brings me to 1. So this function, once I reverse the components, once I reverse the inputs and outputs, I get a function as a result. So we say that f has an inverse that's a function. And therefore, f is 1 to 1. Okay? So the inverse of f, and I think after what we did on Wednesday, we could actually tell right now, how would I write the inverse of f? X, what'd you say, Colin? Yeah? Yeah? And what would it look like? What would be the actual inverse? What's happened to x up in the original function? Oh no, not doing all that. Just what we did. Just what we, yeah. Just what we did on Wednesday. That little thing we did with the shoe and the sock and all that. So what's happened to x in the original function? Yeah, so how do we undo that? Right, so what would our inverse function look like? X minus 1, right. So there's my inverse function. We notice that this produces, for every different input, we get a different output. And this means that the inverse of f is a function. This is definitely a function. So it has an inverse that's a function. And if it has an inverse that's a function, what does it tell me about the original graph f? It tells me it is 1 to 1. F is a 1 to 1 function. And if you look at f, for every single input, if you go to anywhere along this x-axis and you go to the graph, you come to 1 and only 1 output. That makes the graph of f, the function f, 1 to 1, which tells you it definitely has an inverse that's a function. That's what it tells you. I have an inverse that's a function because I'm 1 to 1. All right. So we're looking for monogamous functions, right? No, that was a joke, sorry. Can't put this on YouTube, I guess. Okay, so here are 4 possible solutions for g of x. Now we're looking at the purple function, the purple graph. So we have -2 going to 9. We're used to it being -3 going to 9, right? But it's moved to the right 1. So -2 goes to 9, -1 goes to 4, 0 goes to 1, and 3 goes to 4. So this is definitely a function because each input has 1 and only 1 output. And now we reverse the components. So we reverse the components, and now we're saying for this function, certain inputs produce the same outputs. So if we look at 4, 4 is going to -1, and 4 is also going to 3. So this function, this set of 4 ordered pairs is a relation. It's not a function. So what do we know? We know that this has an inverse, but it's just a relation, and it's not 1-to-1. And the way you can tell that is you go back to your picture, and you can see that if you pick different inputs and you go up to the parabola, you're at the same height, you have the same output. So that is not 1-to-1, because 1-to-1 says if you have different inputs, you have different outputs. So this is not a function, and it's not 1-to-1. So that's what we want to conclude from this. G is not 1-to-1 and does not have an inverse function. Okay? It's not 1-to-1. All right. So now let's see, if you turn the page, all the little funky little graphs I just drew here are really drawn nicely here. I would just put little arrows on here to make Shannon happy, right, Shannon? And we would denote the straight line as F. Okay. So when we swap the inputs and outputs for our two functions, f and g, we noted that the inverse of the linear function, which is a straight line, is a function. However, the inverse of the quadratic function was not a function. So now we want to know, can we just visually look at the graph of a function and tell whether or not it has an inverse or whether it's 1-to-1? So we can do that by drawing any horizontal line through our graph. So let's just draw a horizontal line. Y equals 4 is a horizontal line. So let's just draw it straight through. Well, start a little too low. Let me start here. Straight through 4. Oh, almost straight through 4. Let me see. Lower it. There we go. Okay, so we draw a horizontal line. Y equals 4. Straight through both graphs. And we ask a simple question. How many times does the graph intersect my straight line? Just once, right? It intersects F once. Okay. How many times does it intersect the graph of G? Twice. So that's your visual test right there for whether a function is 1-to-1. If you draw a horizontal line through the graph of a function and it intersects it twice, or 3 times, or 5 times, but more than once, then you know it's not possible for that to have an inverse function. Because look at this, you have 2 points right here. 2 points right here, 3, 4, and -1, 4. When you reverse those components, you're going to have 4 going to 2 different outputs. So this function, g, is not considered 1-to-1. So that's all you have to do when you're looking at a graph to tell whether your function is 1-to-1 or not. We call this the horizontal line test. Or we get a little lazy and we say HLT, horizontal line test. So don't confuse the horizontal line test with your vertical line test. Your vertical line test will tell you whether something's a function. The horizontal line test tells you whether it's 1-to-1. And if it's 1-to-1, it has an inverse that's a function, and we're all happy campers. Okay? That's a relation. Exactly. That's right, Mackenzie. That's a good summary. Okay, so let's take a look. We've played around with this whole idea of finding the algebraic inverse for a function on Wednesday just by looking at this function here, for example, and saying, what's happened to x? And I'm going to reverse the order of what's happened to x, and I'm going to take the inverse of, I'm going to undo every single step. And we just did it verbally. The book shows you how to do what we did verbally on Wednesday with a series of steps called switch and solve. Okay, and we're just going to practice that today. for a couple of examples, one in the demo, and you'll have a chance to do it twice in your activities. So we first begin, before we even try to find the inverse for a function, we first see if it's one-to-one. If it isn't, we're not going to bother because it's not going to be a function. So we usually look at our function, and hopefully we can get a picture of it in our mind. And if we look at f of x equals 5x minus 6, what kind of picture is that? What kind of picture does the graph give us? A linear picture, right? And it's not a horizontal line, right? And it's not a vertical line. If it was a vertical line, it wouldn't be a function at all. But 5x minus 6 goes through the y-axis at 0, -6, and it has a slope of 5. We're kosher, right? If we draw horizontal lines through that, we only touch that graph in one spot. So yes, it's one-to-one, passes the horizontal line test. HLT, we're golden. Okay, so we know, if we look back to the lecture, the first preview exercise you did on Wednesday, you had an equation solved for x, and we solved it for y. And that was to give you a little bit of experience with what we're going to do today. We know that we switch the x and y components when we look at the solutions for the inverse function. So we're going to start off by writing our equation as we normally would. We would replace f of x with y. And we know that our inverse function now will be solved for x. So, but not x, this is already solved for y, and we say, okay, we're going to switch the x's and y's, so why don't we just do it right at the beginning and then go through a series of steps to undo what's happened to x right here. So the next thing you do is interchange the role of x and y. This is the switch part of the switch and solve strategy. We're just going to switch x and y. We're going to, where we see y, we're going to write an x, and where we see x, we're going to write a y. Now we solve this for y. So we're going to undo it, and then our equation will be written in functional notation in the end, because it will be written in terms of x, which is how we like to see our functions. So to undo this, the first thing I do is to add 6 to both sides, and then I divide both sides by 5. Okay. And now where I see y, I say this is my inverse of f in terms of x, because this expression right here is all in terms of x. If I didn't do the switch at the beginning, I would have done it at the end, because I want to write my inverse function in terms of x. So this is my inverse. I think I have to prove it. How do I prove it? Well, the only way to prove that two functions are inverses is to do what we did on Wednesday, is to compose them and hope that the result of the composition comes out to be x. And then we reverse the order of the composition. And if that comes out to be x, we know we have truly two inverse functions. So it doesn't take long to do. You just have to remember the two steps. So on this side, let's compose f with its inverse function, and see question mark whether it comes out to x. And then we reverse the order of the composition. So the inverse function's on the outside and the function f is on the inside. And let's see if that comes back to x. And just in case you forgot, f of x is 5x minus 6. So we're trying to prove that these two functions are truly inverses of each other. Okay, so let's do it. So let's take our first composition here. So where I see f inverse of x, I'm going to replace it with what f inverse of x is, which is x plus 6 divided by 5. And the question is, does that come out to be x? Okay, so this tells me that I look at my f function, and everywhere I see an x, there's only one spot. I replace it with this little expression that we think is the inverse of f. So I go back up here to f of x and I say, okay, f of x says to take my input, which in this case is x plus 6 over 5, multiply that input by 5. So I'm going to multiply it by 5. And then I'm going to subtract 6 from it. And I'm going to simplify this and hope that it comes out to be a baby x. So my 5's cancel, and I get x plus 6, take away 6, and that gives me x. I'm half of a happy camper, okay? Because guess what? That doesn't prove anything. I have to show it both ways. So at your seats, see if reversing the order of the composition brings you back to x. Is this okay? Did it come back to x? Yep, let's take a quick look. So I'm going to put f of x in for x in my inverse function. So here's my inverse function. Where I see x, I replace it with f of x. I add 6 to it, and I divide by 5. Now, f of x, I replace f of x with what it equals. It equals 5x minus 6. That's what f of x is. I add 6 and divide by 5. 5x over 5 is x. Life is beautiful. Okay? That's how you prove that those two functions are inverses. So next week, on your quiz on Monday and your test on Friday, if I asked you to prove that two functions are inverses of each other, this is how you do it. This is the only way you can do it. Okay? So if you came in, okay, today we're finishing up our new material. The only material we have for our next test is from class 12 to today. 3 of those classes were all on the same topic, transformations, and the last 2 topics were all on inverse functions. Okay, so our test will be next Friday. Monday's quiz is one of those half in class, half with your group, and half individual. If you're here late, your only choice is to do it as an individual. You're not going to join a group midway through and, work on it. Now, I think someone said to me, I can't remember if it was this class or my 840 class, if you don't like working in the group and you just want to do your individual and have that count as the whole thing, that's fine as well. My purpose of giving you the group quiz is so that you can work out whatever areas you may still have questions on. But if that's not how you want to do it, that's fine with me. The other thing is you can still bring in an index card with some notes on it for the quiz. Even if you're taking part of it in the group, you can still use that. Those are on my door if you need them. Okay? So everything still applies. All right, so let's take a look now at what we're going to do today. We're going to have some class activities. And when you come down to this number 3, I want you to do a couple of things for me. I want you to draw a picture or draw a graph of your function once you restrict the domain, and you'll understand that in a minute when you work through this. Once you have a restricted domain, once you restrict the domain, I want you to draw a picture. So you're going to have a picture here of F, and underneath here I want you to list the domain, represent the domain and the range. Then over here, beside it in this space, I want you to graph the inverse of F, and I want you to write the domain for the inverse and the range for the inverse. So I just want to add a little bit to that exercise. Oops, this is just F. Okay, just a little bit. Because there's some important things to see, and without writing it out, sometimes we don't bother to do it. So here's going to be a graph of F. This is its inverse. I think there should be enough there to keep you busy. If not, after I've checked everything, start working on your study guide. That will help you for Monday as well. This function is not one-to-one. It doesn't pass the horizontal line test. So it's not one-to-one. And How could you see that it's not one-to-one algebraically? This is important. If you tried without a graph to do your switch and solve strategy for this, and you went like this, and you solve this for y, what's going to happen? Well, you're going to start this process, and the minute you see this, you have to remember that when you undo that squaring, you get two answers, positive and negative square root. Because when you literally put the square root around that, you have the absolute value of y. I mean, we've been talking about this forever. So you don't just do this, you have to do this. And this is what shows you that your inverse function, not only does this picture show you that the inverse of this function is not a function, but this shows you right here. Because this says, give me an x, and I'll give you two y's. All right? Houston, we have a problem because this is not a function. You can't have your x value go into two different y's. It has to be unique. So if you tried this algebraically, it supports what this picture shows you. All right? So the way we get around this mathematically is we restrict the domain for a function like this. We say, I'm going to look at finding the inverse for this function, f of x equals x squared minus 1, and you can say when or for when x is greater than or equal to 0 if you choose. And when you do that, you literally take away that part of the parabola, and now you have a one-to-one, okay? Or you could say, I'm going to find the inverse for this function when x is less than or equal to 0. And then you're taking away, well, before I wrote that, I should have done Control Z. Let's see, it's not going to let me. Then you're taking away the right-hand part of the parabola, the right half. Okay, once you do that, let's suppose we take a look at restricting the domain like this. I'm going to go this way. So I'm going to look at this function, x squared minus 1 when x is less than or equal to 0. The domain for this function is negative infinity to 0, including 0. And what's my range? Negative 1, because that's the smallest output value, all the way up to infinity. Now, when I take the inverse, when I do the switch and solve strategy here, my inverse function looks like this. I'm looking at, oops, right? Is that correct? All right. Now, what does this picture look like? Something like that, right? Or if you put your line in like here and you reflect it. This is all your output here is negative, right? Or non-negative, because it does have the point negative 1, 0 here. So what's the domain for this inverse function? Where does it start? Where do your x values start for this inverse function? Domain, folks, where does this start? Negative 1 to where? Infinity, right? Look, folks, the range of your function becomes the domain of your inverse. And what's the range of this function? The inverse of this, right? Okay. All right, so that was what I wanted to show you. That's a lot of information there. There's a lot, that one problem, 3A, B, and C, there's a lot to digest. Pay attention to it. Think about it and look at it again Sunday after you watch the paper.